The big loop is going to give us the most sensitivity.
So we start out with the big guns, right?
Exactly, yep.
Hey there, welcome to Embedded Toolbox, the video interview series where we try to save the world by solving one engineering challenge at a time. And one of the biggest engineering challenges that a lot of developers face these days is with EMI emission. And in order to address some of those design issues, we've brought on Rich Markley, who is a product manager at Rohde Schwarz. How you doing today, Rich?
I'm doing great. Thanks, Brandon. Thanks for having me.
Sure thing. So what's the nightmare scenario with getting to EMI emissions testing and then you fail? What happens?
Yeah. So I mean, definitely the nightmare scenario is you go in for your compliance to pass that and you don't pass. And as you can imagine, you're going into a area that's very expensive, potentially thousands of dollars a day to get your product tested. And to not pass not only adds time to your schedule, but also adds pretty significant cost as well. We're going to be looking at essentially a scenario where you didn't pass. And so if you didn't pass, one of the best tools to be able to look at that is an oscilloscope. And so we're going to be pulling out an oscilloscope. We're going to be using some near field probes and basically sniffing for those emissions and trying to narrow down what's causing the problem.
All right, Rich. So obviously that's the scope in front of us here. What is the setup you have with this board in the near field of the screen?
Yep. So basically what we're going to do is we've got the oscilloscope set up. We've got a set of near field probes that we're going to be using. I've attached those to channel 1 here. The near field probes, it's got a group of both magnetic probes and E-field probes. So we'll kind of walk through those here in a second. So we're going to be using our RTO2000 oscilloscope. So the RTO2000 goes up to 6 gigahertz of bandwidth. It's got up to 20 gig samples per second sample rate. Pretty deep memory, very sensitive front end, very low noise. So it's really well situated for doing EMI debug. So what we're going to do in the first example here is we're going to actually step through locating an emitter. And so in this scenario, this basically assumes that you failed in your compliance testing. You know what frequencies you failed at. And so now we need to find out where that's coming from. And traditionally, I mean, the designer is going to have a really good feel for their board. They're going to know what their clock frequencies are. They're going to know what the harmonics are that they should be looking for. But in this example, we're going to pretend that we don't know. And that we're going to sniff all around the board and try to find where that signal's at. All right, so the first thing that we're going to do is typically when you start to try to sniff for this, and we know that we're looking for a 10 megahertz signal, you have to set the scope up. We want to make sure that we're in 50 ohm mode. We're using the near field probes. I'm going to go to a very sensitive setting on the oscilloscope, all the way down to about 1 millivolt per division. And the reason for that is the near field probes are not amplified. Where some of these signals that we might be looking for could be pretty weak emissions, and so we want to have as good a sensitivity as we can have while still having the full bandwidth that we need. I'm going to start with our biggest loop. The big loop is going to give us the most sensitivity to try to narrow down the area on the board, and it's a great one to start with, and so we'll go ahead and start with that one.
So we start out with the big guns, right?
Exactly, yep. And so we'll go ahead and hook that one up. Now I need to turn on my FFT, and so we're going to go in, because we know that this is at 10 megahertz, I'm going to go ahead and set my center frequency right at 10 megahertz. I'm going to go ahead and change my resolution bandwidth down to something like 20 kilohertz. And we'll go ahead and turn that on, and we're going to take that big gun, and we're going to start searching around on the board. And what we should see is when we get near that signal, we're going to see a spike at 10 megahertz. And so as we kind of sniff around, you can see we're starting to get closer to it. And as we get closer to the chip here on the board, we can see that we're getting pretty strong emission on that at that chip itself. And so you can see in the frequency domain now, pretty obvious that we've got something right at 10 megahertz. And so this is what we were looking for. This is the area that we wanted to find. And so now we've kind of narrowed down the area. Now let's see what we can do to narrow it down to the exact signal that's causing the problem. And so now I'm going to switch from my big loop into a smaller loop. And so as you can see, the smaller loop is going to give us a little bit more specific area that we should be looking for on the board. So now we're going to take, and we know that it's in kind of this area right around that microchip there. So now let's see if we can figure out where on the chip we need to be looking at. And so I'll go ahead and dive in here. We're going to start on kind of the right-hand side, and it's pretty strong, but as we start to get over here on the closer to the left hand, bottom left hand, it starts to get a lot stronger. And so now we know that, okay, on that chip, it's probably in that bottom left-hand corner. And so now with these near-field probes, we have another magnetic probe that we can jump into that's even more sensitive and finer kind of look. And so we'll grab this one, and it's hard to see, but it's actually got a little loop there. And this is going to allow us to kind of almost get down to the pin on the chip to be able to determine where the problem is at. And so as I come in here, we'll go ahead and start to look down in that bottom left-hand corner. And we can pretty quickly see that it's very much in that bottom left-hand corner, right in there, maybe going to that coupling capacitor. And as I move away from that, it gets a lot weaker. And so we know that it's now right down in that area. And so now I can pull out one of my E-field probes. And the nice thing about the E-field probe is I can actually sit this down right on the traces themselves. And when I sit it down right on the trace itself, we can determine exactly what trace is causing that problem. And so as I come in here now, I'm going to start, and it may be a little difficult to see, but I'm going to start hitting this right on some of those traces. And you can see, boom, when I get on that trace that's coming over here to our little oscillator on the side, our clock chip, you can see that we have a very strong emission right there. And so that's where our problem is at. And we've now narrowed it down to that exact trace.
Wow, I mean, this is great. I mean, you got this super precision all the way down to a specific trace, and here we've been talking about this for just a few minutes, right?
Yep.
Awesome. Now, one thing, Rich, that I notice here is that on the screen share, you have both the frequency domain and you have the time domain up there, and we were mostly focusing just now on the frequency domain and using that to identify your EMI issues. How can the time domain be used to help with a similar sort of task?
Yeah, absolutely. Great question. So I'll switch gears a little bit and kind of show you a different setup here. This board has a power supply on it as well. And so power supplies are one of the biggest emitters and one of the biggest problems that people typically run into. So on this one, what we're going to look at is, like you mentioned, we're going to look at it in the time domain and in the frequency domain. And so I'm going to go ahead and restart. And to restart, I'm going to go back to my 50 ohms. I'm going to go ahead and leave it at 50 millivolts per division. So this one is a really strong emitter, so we don't need the sensitivities that we were using before. But we are going to go and we're going to look at it from a little bit higher bandwidth. And so when I set up my FFT, now I'm going to go ahead and put my center frequency at 500 megahertz. And I'm going to go ahead and put my resolution bandwidth at something like 20 megahertz. And I'll go ahead and turn this on, and you'll pretty quickly see as I dive in, we get a really strong emitter and a broad shoulder that pops up in the frequency domain that you can see. And this is going all the way from down at, tens of megahertz all the way up to 600 megahertz on the display itself. And so you can see that this is, as I mentioned, it's a very strong emitter. One thing I'm going to do is I'm going to go ahead and dial that back even a little bit more on my sensitivity. And I'm going to put a little bit more time on the display as well. And you can actually see these little bursts of energy that are happening that we're capturing with that near field probe. So one of the most powerful things that I've found is it's often easier to see issues in the frequency domain.
Right.
And when you can see them in the frequency domain, sometimes it's difficult to pick them out in the time domain until you can correlate those two things together. And one of the things that we can do is we can actually set up a frequency mask and say when that mask is violated, I want the oscilloscope to go ahead and stop and basically trigger. And so I'm going to go ahead and set up a frequency mask kind of roughly in that area where that broad shoulder was at. And I'm going to tell the scope when that happens, I want it to go ahead and stop the acquisition on that violation. And so now when we come in here, and you'll see here in a second, as I capture, and let me go ahead and get it to to stop on that. I'm going to go ahead and tell it to stop on that violation. So now when we come in here and we get any part of the signal that violates that mask, it's going to go ahead and stop the acquisition. And when we stop that acquisition, we can see that information correlated in the time domain.
Right.
And what's really neat about that is it might be, let me go ahead and turn up the intensity here so you can see it a little bit better, but there's a little burst of energy right at the trigger point where we stopped because of that violation in the frequency domain. And if we want, we can actually take this a step further. And now I can go in and for my frequency domain, I can actually set up a gate on that. And the cool thing about a gate is you can now see we have this little window of time up above. And as I move that window of time, and so I move it off that burst of energy, you'll notice that we don't really have anything happening, or we don't have any strong presence in the frequency domain. As I move that gate over that burst of energy again, you can start to see that's where our big shoulder starts to step in. And I can go a little bit further, look at this next burst of energy in the time domain, and you can see same deal, that's causing that burst of energy. And so this is a really powerful tool for somebody to be able to correlate something from the frequency domain back to the time domain, so then they can start to debug from that perspective and hopefully shut down that emitter.
I'd really like to have you back and talk about some low-speed serial debugging. But until that time, where can people go to find out more information, Rich?
Yeah, so go to our website, so Rohde-Schwarz.com, and you can find all of this information out there.
Very good. Well, thanks again. Take care, Rich.